Hey y'all, today we're going to be talking about finding limits graphically. So limits graphically is kind of the intro. It's the first lesson with limits. So whatever you did last year, don't worry if you don't remember limits very well. I'm going to start all the way from scratch. So first off with limits is we evaluate limits not just as a number. A limit is not what the function is equal to, but what the function looks like it's equal to. It's what the function looks like it's approaching. So we read a limit that as x approaches some number, what y value does the function look like it is equal to or look like it's approaching? So to help evaluate this, sometimes we actually look at the limit from the left side or from the right side. So the limit as x approaches 1, and this little negative, this doesn't mean -1, but it means the limit from the left. Okay. Likewise, limit as x approaches 1 from the positive. Okay. It's not +1. It means from the right. And then the limit as x approaches 1 without the negative, the positive, is combining these two together. So I take whatever those two are, and I use both of them to evaluate the limit is at or as x approaches 1. So as it says, it will only exist if the limit exists from both sides and is the same. So if the left side, let's say, was 2 and the right side was 3, the overall limit would not exist. Okay? If the left side was 2 and the right side was 2, then the overall limit would equal 2. So we need both sides of the limit for the overall limit to exist. So as a couple of examples, limits kind of follow through a lot of our different rules of addition, subtraction, multiplication, and whatnot, just like any other function would. So if I have the limit as x approaches some number of f of x plus or minus g of x, that's equal to f of that number plus or minus g of that number. So we just plug it into both functions, add or subtract them together, whatever is being asked. If I have the limit as x is approaching some number of f of x divided by g of x, I'm going to evaluate f of x, and I'm going to evaluate g of x, g of that number, and then I'm going to divide them to get my limit. Okay, if I have the limit as x approaches some number of f of x times g of x, f of that number times g of that number. And then last but not least, if I have the limit as x approaches some number of f of g of x, remember this is our composite function, then I evaluate g at that number. And let's just say that g of that number equals, let's call it a. Then I evaluate f of a to get what my limit would be. So the composite one's a little bit weird because we have to do g first, and then we're going to evaluate f at whatever we got for g. So it's almost like two problems in one. But the general gist is you plug in the number, you evaluate the functions just like normal. So let's actually look at some graphical examples. We have the example over on the left. So we have a nice little cubic function, but right here in the middle at 1, we have that open circle, which if you remember from last year, that open circle represents a hole. So the limit as x approaches 1 from the left, what we're going to do is we're going to go from the left and we're going to follow our function. So as our function comes in from the left, what y value does it look like our function approaches? So as we get closer and closer and closer, our function looks like it gets to 2. So we say the limit from the left would be equal to 2. All right. Our other one, limit as x approaches 1 from the right. So once again, we do the same thing, but this time we come from the right. So we follow our function from the right. What y value does it look like it gets to? Once again, 2. So we say the limit from the right is also 2. Now, since the limit from the left and right were 2, that means the overall limit does exist and it is equal to 2. Now, conversely, if I ask what f of 1 is, so if I ask what the actual value of the function is there a point right here? No, there is not a point right there. So we would say undefined. Okay, just as a general rule, functions are undefined. Limits do not exist. Or D&E for us short math folks, because we like to write as few letters as possible. All right, let's look at another example. So we have g of x. We got a function coming from the left, a function coming from the right. The discontinuity we have going on here, think about it as if I was following my function to get from here to here, I was going to have to jump. So this is a jump discontinuity. We still have a hole, but we have a point that kind of comes in and fills in the hole in the track of the function. So the limit as x approaches -1 from the left, so we're going to follow our function from the left side. What y value does it look like it gets to? It looks like it gets to 3. So our limit from the left would be 3. The limit as x approaches -1 from the right, I'm going to follow my right-sided function. What y value does it look like it gets to? It looks like it gets to -1. Now 3 and -1, are those the same value? They are not. So that means our overall limit does not exist. So the left side and the right side were not the same, so our overall limit does not exist. And just like we said up above, functions are undefined, limits do not exist. Now, last but not least, if I asked you what g of -1 is, well, here at -1, while we have the hole, we also do have a point that's accounted for here. So if I were to plug x equals -1 into my function, I would actually get a y value out, and that y value would be -1. So just to kind of look at the two, if there's a hole and there's no point to make up for the hole, then the function is going to be undefined. If there's a hole, but there's another point to cover up for that hole, then the function is going to equal whatever the value of the point is. So let's look at another example. This time we have a nice function. We have a hole in the middle, just like we had in the first example, but now we just have a point floating out in space by itself. So our limit as x approaches 2 from the left. What y value does it look like we get to? -1. Our limit as we approach 2 from the right. What y value? The exact same one, -1. The left and the right side limit are the same. So that makes my overall limit -1. And then h of 2, okay, what do we have going on here? Well, we do have that hole, but we also have that point that makes up for it. So if I'm evaluating the function, I always go to the point, not where the function looks like it's going. So the point is at 2. So h of 2 would be equal to 2. Right, last but not least, we have asymptotes. So this is a good old-fashioned rational function. You did this towards the beginning of the year last year in pre-calculus. So we're going to be looking at this vertical asymptote right here. So as we approach the function from the left of 2, so as we approach the function, what's our function doing? Well, it's shooting up forever, right? It's going to keep going up and up and up. Well, what's all the way up at the top of forever? Well, positive infinity. So as we approach from the left, the limit is equal to positive infinity, right? As we approach from the right, same exact thing. So as we go up and up and up, what's it going to be? Positive infinity. Now, are these the same thing? Yeah, but does it kind of almost sound weird to say an infinitely huge number is equal to an infinitely huge number? Yes. So you can actually say infinity or D and E. College Board will accept both answers. So if on a test, there will never be both of those to try and trick you. They'll either put D and E or they'll put positive infinity. So don't feel like you have to decide between the two on multiple choice. And if it was a free response question, you could just put either and I'd accept both. Okay. Now J of 2, at 2, what's happening? We have that asymptote. Is an asymptote an actual point on a function? Nope, it's a spot on the function where we can't actually go. So J of 2 would be undefined. Okay. Then our limit as x approaches infinity. So which direction is infinity for x? Well, it's going to be out towards the right. Well, what y value does it look like our function is approaching as we go to the right? Now, you might say, well, Mr. Arbona, it's going to keep going down. But what's there? There's a horizontal asymptote. Do our functions typically cross our horizontal asymptotes? No, they're typically guided by them. So if it just kept going, it's going to get closer and closer and closer to the horizontal asymptote without ever touching it. So what's the y value of this horizontal asymptote? 0. So we'd say our limit as x approaches infinity is 0. Now, conversely, as x approaches negative infinity, that's going to be out towards the left x values. Our function is doing the exact thing. So one thing to notice about rational functions is that as they go out towards positive or negative infinity, they're always going to approach their horizontal asymptote. Nice little fun fact. All right, on this one, we're going to sketch the graph and then find the values of our limit. So we have x squared plus 1. So we'll go up to 1. And it's just a nice little parabola. And yes, I realize that this is a quadratic function. We'll get to that in a little bit. And then I'm going to change my color for my other one. So we have x plus 1, nice little linear function, slope of 1. And no, do not feel bad if you did not know how to graph those. You will not need to graph things by hand for the AP exam. It is always useful to know how to graph things, but it is not necessary to know how to graph things. Okay, so those would be our two functions if we were graphing them fully, but what do we have? Well, we have a restricted domain because this is a piecewise function. So x squared plus 1 is only going to exist for values greater than 1. So what I'm going to do is I'm going to take away the rest of this for any values that are less than 1, and I'm only going to graph it for values that are greater than 1. So over there. Kind of just that little half of a curve. And then at an x value of 1, is this function actually able to equal a y value at 1? No, because 1 is not included in the domain. So right here at 1, I know you're probably like, Mr. Arbone, this is so small. We're going to put a hole for our parabola. Okay, now our linear line is for x values less than or equal to 1. So anything to the right of 1, I'm going to erase. So all of that, any values greater than 1, we're going to erase. We're going to keep everything to the left of 1 equal to that right there. And then this function is able to have a y value at 1. And that y value at 1 was 2. So I can put a point right there. Now, nice little fun thing that occurred. The hole that occurred on our parabola got filled up by the point for our linear line, which now means we have a point everywhere along our domain. So we have this nice little connected graph, which is cool and useful. But let's talk about what that means for our limits. So our limit as x approaches 1 from the left side. So as we approach from the left side, what y value do we look like we get to? It looks like we get to 2. As we approach from the right side, what y value does it look like we get to? It looks like we get to 2. Pardon my not really great graph. And then if the left and the right are the same, that means the overall one is 2. And our of 1, so you can look at the graph. We definitely have a point there. Even though there was a hole, the point covered it up. So the y value is 2. But if you don't quite trust me, well, let's just look at our domain. Which of these functions includes 1? Well, it's our x plus 1. So I can just plug that in. So r of 1 is equal to 1 plus 1, which is equal to 2. So sometimes it's nice to have nice little algebraic math back up our graphical math. All right. Last thing I'm going to talk about with you in the notes is finding a limit from a table. So sometimes they might give you the information or the values of a limit from an actual table. So we have f of x is equal to x cubed minus 1 over x minus 1, a nice little rational function. And then they want us to find the limit as x approaches 1 of the function. So looking at our table, as we get closer and closer and closer to 1 from both directions, so 0.9, 0.99, 0.999, that's going to be from the left. And 1.1, 1.01, 1.001, that's going to be from the right. So as we approach from the left and the right, we're going 2.71, 2.9701, 2.997, and then 3.31, 3.0301, 3.003. So if we were just to take a guess, what Y value would you probably think we're getting close to? Well, hopefully you're thinking we're getting close to 3, okay? And you'd be correct. It looks like we're getting really, really close to 3. Now, as it says over here on the right at 1, what's happening? Well, more than likely, looking at our function, we probably have a vertical asymptote or a hole occurring right there at 1. I'm not doing any actual division or anything, so I don't know which one it is, but we probably have a vertical asymptote or a hole, which is why we're getting that error right there, which is why it's saying this method is an approximation. We don't have a graph to confirm it. We don't have an actual point there to make it nice and easy and get a value out. But looking at the data we have, we're probably pretty sure it's going to equal 3, which that's really the usefulness in a limit, is that even though we don't have a value there at 1, we kind of have a pretty good feeling of where the function is going to go. So a limit's a nice way for us to approximate the value of a function without actually knowing what the value of that function is. Okay, so fill out the rest of these notes on your own, y'all, and then you're going to be working through the limit stations today in class. Thank you for your time. Good morning, y'all. So today we are going to be talking about limits day 2, continuity, and IVT. IVT stands for the intermediate value theorem, but we'll get that in a little bit. But first, we're going to talk about continuity. So we have 2 different functions. So the function here on the left is a continuous function. So notice how it's smooth and continuous, no breaks, no holes, nothing funny, anything going on. Function over on the right, g of x, is a discontinuous function. So it's probably piecewise. We got lots of different little pieces of functions going. We got a jump discontinuity. We have a removable discontinuity. We have another jump discontinuity, and we have a removable discontinuity. So we got holes, we got breaks, we got asymptotes, all different things that can cause a continuous function to be discontinuous. So when I want to talk about continuity at a point, what does that mean by continuity at a point? Continuity at a point means to prove a function is continuous through that point. So let's say I wanted to prove continuity right here. Well, looking at it graphically, y'all would probably tell me the same thing we decided earlier, that f of x is continuous. So yeah, it should be continuous at x equals 0. Okay. We can see it graphically. Graphs are easy, but remember, we talked about this a little last class with our graphical limits. Graphs are not perfect. They are an approximation. What is not necessarily perfect, but what is more truthful, it's going to actually prove things, is that algebra, is that actual proof that when I plug in numbers, I can prove that something is continuous. Okay, so if I want to show that a function is continuous at a point, there's 3 things I have to show. So let's say that point is x equals c. Then the first thing that I need to show is that f of c exists. So it doesn't matter what it equals. I just need to show that when I plug a value c into the function, I get a number out, which means that that point exists. Okay. The second thing that I need to show is that the limit as x approaches c of f of x is, sorry, I always mix these up. So going back a bit, f of c is defined and limit as x approaches c of f of x exists. Okay, they kind of mean the same thing, but we do use a different language for a reason. So f of c is defined is our first step. The limit as x of c, x approaches c of f of x exists. So our point is defined, our limit exists, and then the third is that we have to show that whatever value f of c is defined for is equal to the same value we find for our limit. Okay, so if the point is defined, the limit exists and the point and the limit are the exact same number, then that would make a function continuous at that point. Okay, so let's look at an example. So I want to show that f of x is equal to x squared plus 3 is continuous at x equals 1. So first off, I need to show that f of 1 exists. So what can I do to show that f of 1 exists? Well, I can plug the number in and get a number out. So 1 squared plus 3 is equal to 1 plus 3, which equals 4. So first step, point exists. Second step, I want to show that the limit exists. Okay. Now to show that the limit exists, remember there's two parts to a limit, the left side and the right side limit. Now looking at this function, just if we were to think, do we have anything funny going on at x squared plus 3? No. We can plug 1 in, we already did, and it should be fine. But just for kind of helping you all out sake, when we want to find the limit, if we have anything kind of funny or weird going on, any sort of piecewise function, any sort of hole, something like that, then we want to show the limit as x approaches 1 from the left side. We want to find the limit as x approaches 1 from the right side. And if those are both the same, then that tells us that our overall function is equal, our overall limit is equal to whatever that value is. If those are not the same, then that would mean that our overall limit doesn't exist, which would mean it would fail step 2. So from the left side and from the right side, I can't actually get to 1. So even though I'm approaching 1, I can't actually plug in 1 to see what the limit from each side would be. So 1 squared plus 3 is equal to 4. And 1 squared plus 3 is equal to 4. Those are equal to each other. So the limit as x approaches 1, the overall limit, would be equal to 4. So second step, limit as x approaches 1 exists. Okay. Now, yes, this might seem a little redundant, but that's kind of math. You kind of have to go through all the redundancies. You have to prove that, yes, it's true from every direction. So that it is 100% undeniably true that this function is continuous at x equals 1. So our third step, and this one is more of like, it kind of goes into your answer because this step is either true or not, and it basically gives you your answer. So step 3, f of 1 is equal to 4, which is equal to the limit as x approaches 1. So those are both equal to each other. So then we say therefore, which if you remember from your proofs in geometry, therefore we do those 3 dots in a triangle, which stands for therefore. So therefore, f of x is continuous at x equals 1. Just like that. Okay, now if any of these steps fail, so step 1 fails, step 2 fails, or step 3 fails, then you just go f of x is discontinuous. Also, if any of them fail, you get to stop immediately. You don't have to go through all 3 steps every time. If step 1 fails, you're done. Okay, just move on with the problem. But that is continuity. We're going to practice a little bit more in station 5 and station 6, so don't worry if you're like, Mr. Arbone, that was weird and new. Okay, moving on down, we're going to talk about the intermediate value theorem. So to kind of help you out, what does intermediate mean? Well, intermediate means between. And the intermediate value theorem is essentially a theorem that tells us that the numbers between and a continuous function exist. It's pretty straightforward and simple. Okay. But the intermediate value theorem says that if f of x is continuous on the closed interval a to b, and what that means by closed interval is that means that I'm including a and b. So here at a and b, those points exist, okay? And n So n being this y value right here. So n is a real number. Remember, a real number is just any number between negative infinity and positive infinity, any sort of decimal fraction, anything like that, a real number between f of a and f of b. Okay, so n is some y value that's in between the function's y value at x equals a and the function's y value at x equals b. Okay, so it has to be between them. Then there must exist an x value c in between a and b such that the function at c would be equal to n. Okay, now this kind of seems redundant, especially when you're looking at the picture. Like, well, yeah, Mr. Arbone, if that's my function and n's there, then yeah, there's going to be a c. But remember, graphs are just a helpful tool, but they're not proof. Graphs help us understand the situation going on. So we have to think about this almost without the graph. I covered up the graph in the camera, but obviously that doesn't happen for y'all watching this video. But we have to think about this without the graph and think about this algebraically. So I want to use IVT to prove that there's a root of f of x is equal to x cubed plus 3x minus 2 on 0 to 1. So on that interval. So what would it mean for there to be a root for this function? That would mean the function would have to equal 0 at some time in that interval, because anytime the y value is 0, the x value is a root. Okay. So we have our function f of x equals x cubed plus 3x minus 2, and I want to see if there's an f of c where my function would be equal to 0. Okay, so to do this, I'm going to use IVT. Okay, so for my function to have to equal 0, what f of a and f of b do I have to get? Well, I have to get one of them to be negative and one of them to be positive, because if I go from a negative number to a positive number, then I'm going to have to cross through 0 to get through that number. So let's just plug in our two endpoints. So f of 0 is equal to 0 cubed plus 3 times 0 minus 2, which is equal to negative 2. And f of 1 is equal to 1 cubed plus 3 times 1 minus 2, which is equal to positive 2. Okay. So looking at our math, we wanted to see if f of c could equal 0. So something in between 0 and 1, would that give us 0? We got negative 2 at f of 0 and positive 2 at f of 1. So we had to go from negative 2 to 2. Our function's continuous. It can't break. It can't do any weird jumping. We have to go from negative 2 to 2. So at some point, my function's going to have to cross through 0 to get from negative 2 to positive 2. So I already have all the math I need. So let's kind of put it into an answer. So f of 0 is less than 0, which is less than f of 1. So what I'm showing is that 0 is in between those two. Therefore, there exists an f of c equal to 0 on 0 to 1. Okay, so what I'm saying is because 0 is in between f of 0 and f of 1, there exists an f of c, so an x value in between a and b, where I could plug it in and get 0 on that interval 0 to 1. Okay, so kind of similar to our continuity is that we're going to kind of do our back work. We're going to show, okay, this has to be true, and then we're just going to put that into a final statement there at the end. Let's look at it from a table. So a little kind of different example, but the nice thing about this is I've already given you the numbers. Okay, so given values of the continuous function f of x are given in the table below. Prove that f of x must equal 3 sometime on the given interval. So our given interval is negative 1 to 10. So our closed interval is negative 1 to 10. Okay, so I need to show that at some point from an x value of negative 1 to an x value of 10, my function has to cross through 3. So I want to know what f of negative 1 is, which f of negative 1 is equal to negative 5. I can just pull it straight from the table. And I want to know what f of 10 is. F of 10 is 5, once again, pulling it straight from the table. And then Is 3 in between -5 and 5? Yeah. So for my conclusion, I say f of -1 is less than 3, which is less than f of 10. So therefore, there exists an f of c equal to 0 on the closed interval 0 to 1. Okay, so the table's kind of nice. You don't even have to plug in numbers. That was the easiest, quickest math problem you've ever done. Just a lot of writing. Okay, last thing we're going to talk about, y'all, is finding limits algebraically. Okay, sometimes algebraic limits are super easy. Sometimes they require a little bit of extra work. Okay, but whenever you have an algebraic limit, so I have given you a limit as x approaches c, and I've given you a function. So you have an x value, you have a function to work with. Your first thing you should always try first is direct substitution. So always plug it in first. So the limit as x approaches 3 of 4x squared minus 1. 4 times 3 squared minus 1, that's equal to 4 times 9 minus 1, which equals 36 minus 1, which is equal to 35. So if I plug it in, I get a number out. That's my limit. Nice and easy. Okay. Moving on along. Number 2. Okay. So I still have a function. I still have a number to plug in. Okay. So before I try to do any fancy work, I always want to plug it in, because when in doubt, I always want to plug in that number. Now, eventually, you might be able to start recognizing the situation where you're like, you know what, I think I know if I plug in this number, something weird's going to happen. But for now, we're just going to practice always plugging in a number. Okay. So -2 plus 2 over -2 squared minus 4, we get 0, and we would get 0. Okay, so that doesn't work. Okay, we can't have 0 divided by 0. That's a no-go. Okay, that's what we call indeterminate. We can't have an indeterminate answer. It literally says an answer we can't determine. So that doesn't make any sense. So now, let's see if we can maybe factor and reduce something. So we have x plus 2. My bottom can factor into x plus 2 and x minus 2. So let's get those x plus 2's to cancel out. So now we just have the limit as x approaches -2 of 1 over x minus 2. So now we can plug in again, -2 minus 2, and we get -1/4. Okay, so sometimes we're going to plug in. We're going to get an answer that doesn't work, whether it be indeterminate, whether it be divide by 0, which also isn't okay. We can't divide by 0, or something along those lines. So we have to factor. We have to see if we can simplify somehow to get down to an easier answer. Later on, like at the end of chapter 3, which is towards the end of this year, we're going to learn another way to do this type of question that's going to be super quick and easy. But we can't do that until we learn something else. So don't worry about it for right now. But for right now, plug in the number. If you get something that doesn't work, like a 0 over 0 or divide by 0, then factor, cancel if you can, that sort of deal. Okay. Number 3, when all else fails, think graphically. This will be especially helpful for one-side limits. So looking at this, we have the limit as x approaches 2 from the left side. Okay, so I am only concerned with the left side limit right now. I don't need to necessarily know both limits, what's happening from both sides. Okay, so also looking at it, I know if I plug in 2, I'm going to get 0 on the bottom, but let's do it just, to prove that we're like, yeah, I know this is going to happen, because math always helps you prove things. So 2 minus 2, which is equal to 1 to divide by 0, which is undefined, and that doesn't work. Okay, can't have an undefined limit. Doesn't really make sense. We can have a limit that doesn't exist, but we can't have a limit that equals undefined, because limits aren't defined or undefined. Doesn't make sense. All right. So now let's think about what's going on. Well, it's 1 over x minus 2. It's a rational function. If you were to guess what's happening there at 2, well, it's an asymptote. Okay. So to kind of help us out, I'm just going to draw a quick graph. 1, 2, 3, 4, 5. Okay, and this function would have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 2 from that x minus 2 down here. Okay. And I'm going to cheat just a little bit because I know what this function looks like. Okay, but if you don't know what this function looks like, you can use a graph. I am also going to show you how to still do this algebraically. So don't worry if you're like, Mr. Arbone, I don't know how to graph rational functions. That's okay. You don't have to be able to graph these to do these. Okay, so now looking at our graph, if you were to look at this left-sided limit, where does it look like our function would go to? Well, it looks like it's going to go down to negative infinity, yeah? All the way down there, it's going to keep going on forever. Okay, well, a way that we can actually show this algebraically to prove it, so the limit as x approaches 2 from the left side, I have 1 over x minus 2. Okay, well, let's go ahead and plug in a number to the left of 2. So what's the first number just to the left of 2? Well, 1. So the limit as x approaches 2 from the left side is equal to 1 over 1 minus 2, which is equal to negative 1. Okay, I got a negative answer. Now, we know graphically what's happening. It's approaching an asymptote. So if I'm going negative as I approach an asymptote, as I get closer and closer, what do you think is going to happen? Well, we're probably going to get more negative. Well, let's just plug it in to try it out. So the limit as x approaches 2 from the left side, let's plug in 1.5, just a little bit closer. Well, that's going to give me 1 over negative 0.5, which would be equal to negative 2. If I did a little bit closer, the limit as x approaches 2 from the left side, let's plug in 1.9. So now I have 1 divided by negative 0.1, which is equal to negative 10. So as I get closer and closer, my number is getting more and more negative. Okay? If I got as close as possible, if I plugged in 1.99999 repeating on forever, am I going to get a super huge negative number? Yeah. So super huge negative number, another way to say that is just negative infinity. Okay, and we will talk about this a little bit more next time when we talk about infinite limits. Okay, but when you have a one-side limit as an asymptote, you can plug in a number from that side to know if it's going to be going to negative infinity or to positive infinity. All right, y'all. So we talked about 3 different things. We talked about continuity. We talked about intermediate value theorem, and we talked about algebraic limits. So you're going to be using all 3 in class today. Okay, so go ahead and practice through stations 5 through 8 and ask any questions if you need them. All right, y'all. Today we're going to be talking about infinite limits. And just so y'all know, I'm making this early, so you're not going to have to freak out and do it at the start of class. So yay, Mr. Arbone getting his crap together. Okay. So infinite limits are limits where x approaches positive or negative infinity, especially when we have that rational function situation. So we have f of x over g of x. Okay. And basically any limit, which is that form, is always going to equal the horizontal asymptote if one exists. So horizontal asymptote rules, if g of x has a higher degree than f of x. So that means if I have a situation like so, like x plus 2 over x squared minus 4. Okay, so my g of x, my bottom function, has a higher degree than my f of x. So that means it is bigger on bottom. So what I mean by bigger on bottom is that my degree is bigger on the bottom than the degree on the top, which means my horizontal asymptote is y equals 0. Okay, so bigger on bottom, a nice easy way to remember that is as Bobo. Bigger on bottom, you have 0. Okay, so our next one, if f of x has a higher degree than g of x, so let's just flip that same equation around. So if we had x squared minus 4 over x plus 2, okay, so now this is bigger on top, which we say is bottom, B-O-T, bigger on top, then N for none, because we have no horizontal asymptote. We have a slant asymptote instead. Okay, so the one thing about your bigger on top, if you notice, our general rule is that if the limit is as x approaches positive or negative infinity for a horizontal asymptote, if we don't have a horizontal asymptote, it can't equal the horizontal asymptote. So bottom ones are going to be a little bit weird. So just something kind of to note as we're going through these notes today. Okay, now our last one is if f of x and g of x have the same degrees. So let's say we have x squared minus 4 on top, and we have 2x squared plus 7 on the bottom. So both of these have the same degrees. So we say exponents are the same. Which we can abbreviate as EATS. Exponents are the same. Now for our horizontal asymptote, we divide the coefficients. So remember, our coefficient is this number here in front. Okay, so whatever number is there in front is our coefficient. So in this case, it is 1 over 2. So our horizontal asymptote in this case would be y equals 1/2. Okay, so our three situations are bigger on bottom, so the degree is bigger on the bottom. The horizontal asymptote is y equals 0. If it's bigger on top, then we don't have a horizontal asymptote. We have a slant asymptote. And then if they are the same, if our exponents are the same, then our horizontal asymptote is the coefficients divided. So to help you remember, kind of short little trick, little mnemonic phrase, Bobo Botten eats DC. Bigger on bottom, y equals 0. Bigger on top, none. Exponents are the same. Divide the coefficients. Okay, so let's look at some examples. So the limit as x approaches infinity of x minus 1 over x squared plus 3. So I look at my coefficients. I have 1 and I have 2. So it is bigger on bottom. So horizontal asymptote is y equals 0. So my limit is 0. Notice how I didn't even care whether it was positive or negative infinity. Because it was bigger on the bottom, I just automatically go to it being 0. Okay, so look at another one. So we have 5x minus 2x cubed plus x squared over 3x minus 2x plus 1. So one thing to notice, okay, is not always the first term. It is what we call the leading term. The leading term is always the term with the highest degree for each of our equations. So this one's a little tricky, okay, but I find an x cubed and x cubed. So this is exponents are the same. Divide our coefficients. So our horizontal asymptote is y is equal to negative 2 over positive 3, which is negative 2/3. So that is our limit. Nice and easy like so. Okay, now up here in the top right, we have negative x squared plus 3 over x minus 4. So it is squared over 1, so it is bottom, bigger on top. Okay, so since it is bigger on top, we do not have a horizontal asymptote. We have a slant asymptote. So I'm going to teach y'all just a little quick trick. Yes, it's kind of a cheat code. I can show you the full algebraic method if you want the full algebraic method, but you have to plug in numbers. It's a little bit too much work. So I like my cheat code, and really, as long as you know there's a slant asymptote, that's all that's really important. Okay, so I'm going to make a little graph, and it's going to be the roughest sketch of a graph ever. Okay. So just as a reminder, this is our x-axis, and our y-axis, and this is positive and negative infinity in all of our directions. So just remember, if I went up forever or if I went down forever, that would be positive or negative. If I went to the left forever, that's negative infinity. If I went to the right forever, that's positive infinity. Okay, so looking at this, the first thing I'm going to look is I'm going to kind of guesstimate at what my slant asymptote would be. So you find a slant asymptote by doing long division. And when you do that long division, what you find is that the slope of that slant asymptote follows along with your leading coefficients. So I have -1/1, which is a negative slope. So I'm going to just real roughly act like that's my slant asymptote. Notice I don't have any numbers anywhere. The only thing that's really important to me is that it's a negative slope because I have a negative set of leading coefficients. Okay. The next thing I'm going to do is I'm going to look at which infinity I'm going to. So my x is going towards negative infinity. So I'm going to start here with my function, and I'm going to follow along from the opposite side of where I'm trying to go. So I'm going to go towards negative infinity, and then when I run into my asymptote, I'm going to follow along my asymptote. Okay? So if my function kept going up in that direction, what is it going to go towards? It's going to go towards positive infinity. So my answer here for my limit is positive infinity. Now, you might be right now like, Mr. Arbone, that just looked like a bunch of mumbo jumbo. And you might be a little correct. So real quick, hopefully you can still see my screen. I don't know, maybe you can't. I don't think you can see it, so we're not going to risk it for today. But if you ask, I will show you a graph on Zoom in class on Wednesday or Thursday, proving to you that that is solid math. Okay, but when we are looking at a bottom, there's two things you look at. You look at the leading coefficients to know if you need to draw a negative slant or a positive slant, and then you look at which infinity you're going towards to know if you're going to go from right to left or from left to right. Okay, and then it's just either going to be up towards positive infinity or down towards negative infinity. Okay, last but not least, we have the square root of 4x squared plus 1 over x minus 2. Okay, so this one is super weird because we have that square root on top. But what I want you to do is we're going to kind of cheat a bit once again. Okay, one thing you're going to notice about calculus is sometimes we can ignore things, and it's really like the greatest thing ever. So I'm just going to look at that square root of 4x squared. So if I just look at that, that's technically the same thing as positive or negative 2x. Okay, I don't know which one it is because it's a square root, so I get both a positive root and a negative root. And then I'm looking at it over my other leading term, which is x. So that would be each DC. Exponents are the same because they both have an exponent of 1. So if exponents are the same, then my horizontal asymptote is y is equal to positive or negative 2, because I have to consider both of those points. So as I look at this, you're like, well, Mr. Arbone, if it's approaching two different numbers, then how do I know which one the limit is equal to? Well, we want to know which direction the negative infinity one is going to be, because we're heading towards negative infinity. So if you had a calculator, this would be a really easy one to figure out, because I would either I would just graph it and look at it, and that would be really easy, or I'd plug a number in and I'd be able to get something out. But unfortunately, I don't have a calculator, so we're going to have to think just a little bit intuitively. Okay, so on one like this, I want to know what's happening as I go towards negative infinity. So I don't need to pick, a super huge number, but I do want to pick a number in the negative direction. So let's say negative 10. So I'm going to plug in negative 10 real quick. So the square root of 4 times negative 10 squared plus 1 divided by negative 10 minus 2. Okay, so when I take this, okay, that negative 10 squared, that's going to be 100. So really we get the square root of 401 divided by negative 12. Okay, so what's going to happen is that as I head towards negative infinity, no matter what, because whatever x value I plug in there in the top is going to give me a positive number. So I'm always going to have a positive number under the square root, which is good. I want to have a positive number under square root. But I'm always going to be dividing that positive number by a negative 12. And because I'm going in the negative direction, that square root of 401, I'm really only going to be considering the positive solutions from it. So if I'm always taking a positive number and dividing it by a negative 12, then that's always going to equal a negative number. So which of the two horizontal asymptotes am I going to be approaching? Well, I'm going to be approaching negative 2. So the limit as x approaches negative infinity would be negative 2. All right, let's look at some more. So we have the limit as x approaches infinity of x to the 100th power over 2 to the x. Okay, so before we get going too much on these, all 4 of these situations on this second page of notes are kind of your extraneous. They're a little more difficult. So if you're like, I'm not feeling so hot about these, don't worry about it. Okay, they're not going to pop up as often. So don't feel like you're like, I have no idea what's going on if you don't know these 4. Okay, so let's look at our first one. We have the limit as x approaches infinity of x to the 100th power over 2 to the x. So unfortunately, we can't really compare x and 100 because x is a variable. That doesn't make any sense. So let's go back up to the top right here. As a general rule, factorials are greater than exponentials. Exponential functions are greater than polynomial functions. Polynomial functions are greater than a linear function. And linear functions are greater than logs. What that means is it means if I was to plug numbers into these types of functions, the value that I would get out would go in kind of this order of greatest to least. So logs are our least, factorials would be our greatest. So let's look at the 2 functions that we have here. X to the 100, that's a polynomial. Yes, it has an exponent, but all of our polynomials have an exponent. To the x is an exponential. Remember, what makes something exponential is that it has the variable in the exponent. Okay, so looking at our list, exponential functions are greater than polynomial functions. So what that means is that as I start to plug x values in, eventually over time, as I go towards positive infinity or towards negative infinity, my exponential function is eventually going to be greater in value than my polynomial function. No matter what polynomial function I have on top, an exponential function is always eventually going to be greater, which think about that. Right now, so let's say I plugged in 2. 2 to the 100 would definitely be bigger than 2 squared. Okay, but then 100 to the 100 over 2 to the 100, okay, well now 2 to the 100, it's not that far off. And if I keep going, so let's say 1,000 to the 100 over 2 to the 1,000. So now, yeah, I'm multiplying 1,000 by 1,000 100 times, but I'm multiplying 2 by 2 1,000 times. So that one's actually going to be bigger. And as I get bigger and bigger and bigger, so what's going to happen, kind of think about this as like infinity over infinity plus. This is always going to be a bigger infinity, okay, eventually, because it's an exponential dividing a polynomial. Exponential functions will always eventually be bigger than a polynomial function. So if the number on the bottom is always going to be bigger, and I divide a number on top by an infinitely bigger number, so think about this. If I divide 1 by 2, that's 1/2. If I divide 1 by 4, that's 1/4. 1 by 8, 1/8. 1 by 100. My number is getting smaller and smaller as the number on the bottom gets bigger. So if my number gets infinitely bigger, if I divide something by infinity, it's going to be a really, really, really small number. So we can essentially say it's equal to 0. So anytime the bigger function is on the bottom, then our limit's going to be equal to 0 because that bigger function, that bigger infinity, is going to end up basically getting so big that the function essentially equals 0. Okay, now let's talk about another one. We have the limit as x approaches negative infinity of x to the 100 over 2 to the x. Same function, but now we're going the other way. Now what makes this one a little bit different is that if I plug in infinity to the 100 over 2 to the negative infinity, well, now I have a negative exponent. And before I evaluate anything, I always have to make exponents positive. So we know our exponent rules. A negative exponent means move that exponent up to the top. So we get infinity to the 100 times 2 to the infinity. So now I'm no longer looking at a fraction. Now I'm just looking at a really big number times a really big number, which is just going to be equal to a really big number. So that's actually kind of nice because I don't even have to think about the fraction. I don't have to think about which function is bigger. I just know that it's a big number times a big number. They're both positive, so it's positive infinity. Okay, the limit as x approaches infinity of x over natural log of x. So this time we have a log function and we have a linear function. Linear because it's just x to the first power. So looking back up at our list, a linear function is greater than a log function. So as I kept going, so if I wanted to go to like say 100 over the natural log of 100, well 100 is a pretty big number. The natural log of 100 is always going to be a decimal. Okay, remember anytime we plug a number into a log, a positive number at least, we always get a decimal out. So I'm just going to be dividing bigger and bigger numbers by a decimal. Dividing something by a decimal makes it even bigger. So eventually, this will just equal infinity because the big number is on top of the function. So an infinitely bigger number divided by a smaller number is just going to be an even bigger, infinitely big number. So positive infinity. All right, now last but not least is sine of x. And sine of x kind of operates outside of all these different norms. If you noticed up here, one of the functions we didn't include trigonometric functions. Because what does sine do? Well, for the entirety of a sine function, it goes up and down and up and down and up and down and up like so forever. Because sine functions and really all trig functions do what we call oscillate. They repeat over and over and over and over and over again. Okay, so if it's going up and down and up and down and up and down, is it ever really approaching a singular y value? Well, no, because it's going to go up to positive 1 and then back down the negative 1 and then up to positive 1 and then back down the negative 1. So since it never really equals anything, we would actually say that this limit doesn't exist. Because I can't say it's both 1 and negative 1. That doesn't make any sense. So we just say that it's D and E. Okay. So limits equaling infinity. Remember, we have the ones at vertical asymptotes that we did last class with our algebraic limits. And then we also have our ones at horizontal asymptotes that we did today, our Bobo-Botten eats DC. And then down here you have kind of those extraneous, those weird situations where you have to think about the function on the top and the function on the bottom and which one's bigger. So go ahead and finish out the rest of these, complete these practice problems down at the bottom, and then we'll be working through station 10 and 11 today in class.